Yeah, we'll talk about dimensions and also projections. Okay, what is dimension? Dimension is the minimum number of coordinates you need to represent a point. Okay, let's take this number line. It starts with 0, 1, 2, minus 1, minus 2. This is a line of dimension 1, which means that if you want to represent 2, I just need to tell 2. I can specify the point here. This is single dimension. And if you try to add a complex number, what happens is you need to add the imaginary axis, then this becomes the real axis. Okay, real, this is imaginary, and this becomes I. Okay, and if I have a number like 2 plus 1i, I need to go 2 units in the x-axis, that's the real line, real axis, and 1 unit in the y-axis, okay, and probably specify it. This is 2 plus 1i. So this is what the complex number is with the real and imaginary numbers. Okay, as I mentioned in the numbers video, imaginary numbers is nothing but numbers which rotate. Okay, so that you can kind of take this is I, this is I squared. Okay, if you multiply I again into I, it becomes I squared. Then I squared, if you multiply with I again, it becomes minus 1. Then if you multiply I one more time, it becomes plus 1. So which is what we call it as I squared is equal to minus 1, I cube is equal to minus 1, I to the power of 4 again becomes 1. So it keeps rotating. So I always switches between, this is minus I. Okay, I switches between minus 1, 1, I, minus 1, minus I, and 1. Okay, it keeps revolving around. This is an example of a 2 dimensions. Okay, 2-dimensional number systems. So if you want to represent the length and breadth of a rectangle, this is again a 2-dimension. Okay, this is a 2-dimensional object. You need length and breadth. Even for square, even though the side lengths are same, you need it's a 2-dimensional object. So this is a single dimension. This is a multi-dimensional and 2-dimensional number line. These are all 2-dimensional objects. Okay, if you want to represent a cube, you need 3 dimensions. Okay, length, breadth, and width. Okay, this is a 3-dimensional object. Okay, you need length. Let's say this is breadth, and the thickness we call it as width. Okay, the length, breadth, and width. Okay, it's a 3-dimensional object. So you cannot draw more than 3 dimensions on the board. Okay, so this is again 1-dimensional number line with complex number. It becomes 2 dimensions. This is again 2-dimensional objects, length with side lengths, length and breadth. And this is a 3-dimensional object with length, breadth, and width. Okay, so this is an example of dimension. So in let's take one real world example of how dimensions can go beyond 3. Let's say you have a vector of house prices. Okay, this is house 1, this is house 2, this is house 3, and this is feature 1, feature 1, feature 2, feature 3, feature 4. What these features are? Let's say house 1's, the feature 1 is your the number of bedrooms, the feature 2 is the size of the house, the feature 3 is the proximity to school. Okay, feature 4 is city. Okay, let's say we have denote these 4 features. Then house 1 has a feature like number of bedrooms is like, let's say it's 2, house 2 is 3 bedrooms, house 3 is 4 bedrooms, and size is, let's say it is 100 square feet, this is 200 square feet, this is 300 square feet, and proximity to school, let's say it is 0, which is not proximity to school, let's say 1 if it's proximity to school. Okay, and city, let's say we have denoted by like New York, let's say this is Chennai, this is Bangalore. Okay, just random examples. Okay, just to get an intuition. So each feature is a dimension, and each row represents the price of the house. Let's say the price of the house is like 100K. Maybe we'll keep the New York price higher. Okay, 300K. Chennai is 200K, and Bangalore is 200K. Okay, so yeah, I think This is an example of how different house prices of different cities are captured. Okay, in a matrix and a vector, and each this is dimension 1, this is dimension 2, this is dimension 3, this is dimension 4. Each features contribute or represent one dimension. If you want to represent in a picture, I cannot draw all the 4 dimensions. Just assume that I can draw 3. Maybe the one is the number of bedrooms. The second dimension is the number of the size of the house. The third dimension is probably talks about whether the school is proximate to the house or not, yes or no, so 0 or 1. Okay, 0 or 1. So something like that. I can draw 3 dimensions. So this can go up to n number of features. Actually, you can talk about the safety of the city. You can talk about the safety of the community. You can talk about the how old is that house. Okay, you can talk about how how industrialized is the area. You have a lot of other features you can keep adding, and it can go up to hundreds of features, and that's what we call hundreds of dimensions. Okay, and these dimensions are what you see in the real world examples. If you take an image, for example, okay, let's take an image an example. Okay, let's take this is a photo, a picture, and let's say this is the face. Okay, even though this is a 2-dimensional in terms of representation, each image can be represented into pixels. Okay, a group of pixels. So the pixels has its own length and width. Let's say it has 28 to 28. It becomes 700. What is 28? 728, right? 728 pixels in dimension. Is it 728? Okay. Yes, whatever it is. These are if you have 4K videos or 4K pictures or high resolution pictures, the number of dimensions increases. So if it's just for the simple 28 by 28 pixel, it's very small. Okay, it consumes a lot of dimensions to represent just one simple image. But if we talk about high dimensional images like 4K pictures, like 2048 and 2048, okay, those are like huge number of dimensions to just represent one picture. If you want to process this, it takes a lot of computational time and resources. Okay, that's the reason we introduce the concept of dimensional data reduction. Okay, so what is dimensional data reduction? If you wanted to kind of retain maximum information, but not consume everything as it is, and still make the information relevant and useful, that is called dimensional reduction. Okay, so for example, okay, this is a 3D object. Okay, this is a 3D object. Okay, it's an apple. Okay, you need 3 dimensions to kind of say that it's an apple. Okay, do you really need 3 dimensions to say that it is an apple? Let's project it. The projection is nothing but trying to put some light on top of it and see what it is. Now this becomes a two-dimensional image. Okay, are you able to see? Maybe I'll bring it again closer. Okay, if you see, this is a projection of this apple onto this screen. Okay, and if I am able to tell that it is an apple with 2 dimensions, then that is sufficient for me to kind of represent the information. Okay, I don't need all the 3 dimensions. I don't need the width of the image. Probably I don't need the colors of the apple as well. Okay, I can just draw the outline of it. Okay, let me quickly draw. Like you will be able to tell it, right? If you just draw an outline of an apple, okay, like this. Okay, this is not an apple, but yeah, if I am able to draw something like this, and probably you will tell that it is an apple. Okay, with even lesser dimensions projecting into it. Okay, so yeah, I'm not good in drawing. Okay, just assume that's an apple. So this is what you need to kind of represent an apple. This is what is called dimensional data reduction. Okay, so in machine learning, we'll use a lot of stuff dealing with dimensions, high dimensions, and we'll also use a lot of dimensional reduction techniques. What I showed you is an example of a projection, which means that if I'm able to project a 3D object into 2, it reduces the dimension. Okay, that's an intuition of how dimensional reduction works. and we can expand that idea and talk about more. Okay. Okay. One small correction. This 28 into 28 is 784. I just made a mistake. Okay. So if you take an image of 28 and 28 pixels, okay, it actually is 784 in dimensions. And in machine learning, what you do is you kind of take the 784 and make it into like a single. I mean, you kind of this is a matrix. You make it into a single vector. Okay, if 720 this is 0, and this is like 783. Okay, 0 to 783. This is the number of dimensions you use to represent a single image. Okay, there are multiple ways. If you use convolution neural networks, you don't have to kind of lengthen it. You can just use a convolution map to kind of navigate over the pixels to kind of learn from it. Okay, but yeah, this is what a dimension is all about. Okay. Now let's go to projections. So projections are nothing but trying to represent a vector on the top of other vector. Let's say you have two vectors like this. Let's say this is v and this is u. Okay, and these vectors are very let's say are very close to each other in terms of similarity. Okay, just for sake of drawing, I just drew it a little wider. But let's say it's very close to each other, which means that let's say we have house prices, let's say 100k. Okay, let's say it's a number line. The prices are 100k. And another house price is like 100.1k, 100.2k, and things like that. Okay, and but you have vectors in different, I mean similar magnitudes, but different, let's say different directions. Little bit. I mean not very. I mean very far from the original vector, but little away from it. Let's say you have something like this. Okay, and if you really want to kind of give some if you want to kind of consolidate all the prices and assume that it is all 100, okay, because it is just showing minimal variations in terms of the magnitude and also the direction, it makes sense to kind of consider at an average of 100. Okay, that is why we kind of project. Okay, so we kind of project this vector into this. Okay, let's say this is very close to this. For the sake of drawing, I just drew little bit far. And instead of representing in 2 dimensions, because this requires 2 dimension actually, because you need to know the magnitude and also how many units it's away from the x and y. So you need to know direction also. So if you try to bring this from 2 dimension to 1 dimension, it makes it easy for us to do a lot of computations. So rather than trying to keep all the vectors in 2 dimension and trying to manipulate it, if you are able to project everything into a number line, okay, which is like the v vector, and put all the prices which is like around the number line, then it makes it easy for us to compute the average, then the variation of the the variation of prices, and then the mean, okay, and standard deviation. Everything is easy for us to compute. So this is why you use projections. Another example is like if you have like a security camera, okay, and you wanted to find I mean if you want to find if the face is odd or it is like I mean if someone who is not supposed to enter your office has entered, okay, and each face can be represented like a vector. Okay, and you have, let's say, all the faces you have is represented by this line. Okay, you have kind of an average of all the faces, and there is a small I mean like a new face which is like kind of noted out here. Okay, I mean there may be small variation in the observation. Okay, is it close enough to the existing faces, or is it completely different? Okay, is it really a stranger or someone probably part of your existing mean face? Okay, if you want to find that, you can use these projections to find out how far it is. Okay, basically take a point here and check how far this line, I mean this point is from the average of all the faces, and try to find the anomaly detection, things like that. Okay, this is how projection can be used in real world applications. Now, if you I mean looking at this graph, I mean sorry, this vector once again, you can see that a projection can be represented as like u. This is like v vector. Okay, this is u vector, this is v vector. Okay, and the projection is like this. And if you recollect our unit circle, Okay, you have the radius r. Okay, the length is 1. Okay, the projection is nothing but the amount of I mean, like, the point at which meets the x-axis. Okay, normally is what is the cosine theta, and the point at which this one projects onto y-axis is the sine theta. So this is actually let's say the magnitude of this is u, and the magnitude of this is v. Okay, this is the magnitude of we represent. Okay, this position is like u cos theta. Okay, as we see, this is the rotation of our of the circles. Okay, and which we saw its waves. Okay, this is what happens here. Okay, and this is the cos theta, and this is like this is v sin theta. Okay, this is the magnitude of sin theta. Okay, and if you see, we will deal mostly with the cosine similarities, the projections in this x-axis, because that is where we will try to project. We can project anyways, but we'll mostly deal with this projection. Okay, so now you see, you can write this as like two ways actually. You can write it as a dot product u dot v, okay, which is equal to the magnitude of u into magnitude of v and cos theta. It's the angle it makes between these two vectors. This is one way of writing. Dot product of two vectors is nothing but, let's say you have vectors. Let's say this is this is like 1 unit, 2 units from x-axis, 1 unit from y-axis. Okay, this is like 0 unit from x-axis. Sorry. 2 units from x-axis and 0 units from y-axis. So what happens is this dot product of these two vectors becomes 2i plus 1j, and this becomes 2i plus 0j. Okay. The dot product is nothing but the product of x and y coordinates. Okay, and this is like 2 into 2 is equal to 4, plus 1 into 0 is equal to 0. And the dot product is 4 actually. The dot product of this is 4. Dot product is again, it represents a single, I mean it is a scalar quantity which kind of represents how close these two vectors are. Okay, if the values are high, which means that the dot product is high, which means that the vectors are so close. If the values are very far from each other, then it will be like the dot product will be very low. Okay, or it becomes it becomes like if the vectors are perpendicular to each other or away from each other. Okay, and you can represent this dot product. Dot product can be represented. It's equivalent of this actually. Then with the projection of u onto v and the cosine theta. Okay, now what this can be written as is the projection of, I mean, like dot product u dot v is equal to the projection of u on v. Projection of u on v. Okay, so that is what it means. What is projection of u? Projection of u is u cos theta. So u cos theta and v. Okay, this is what this projection is. Now this is an example of how you can visualize projections. Okay, there is you can also do it through the linear algebra. Actually, this is the way. Using cosine similarity. Okay, and there is one more method you can use it through linear algebra. This is also one way of representing, even though it is dot product is linear algebra. There is another way also to represent the projection. Okay, now how do you? Let's take one more example, intuitive example to kind of make it more clear and concrete. Okay, let's say we have a line. Okay, the line is y is equal to 2x or minus 2x. Okay, there we have a line, which means that when x is equal to 0, y is equal to 0. When x is equal to 1, y is equal to minus 2. Okay, and when x is equal to 2, let's say minus 4. This is the points. And when x is equal to 2, it becomes, when x is equal to minus 2, it becomes 4. Okay, let's say this is 4, this is 8, this is 16 or something. Sorry, 10. Okay, this is the equation of this line. And let's take a point, let's take -2 and 4, which means that this is a point here, -2 comma 4. And we have a point, let's say 1, 2 and 2 comma 10. Okay, 2 comma 10. So this is a vector representation. So we wanted to find out how close this is with this. Okay, or in other words, we wanted to find out the projection of this on this line. So if we try to find out whether this line, this point lies in this line, no, the answer is no, because we clearly say that whatever points, whatever values you give for x, it is just going to keep extending this side or this side. This point is never going to be in this line. And most of the real world examples do not have, I mean, you will not find, I mean, like for example, the phases which you learned, you will not find exactly matching with your with the existing training phases. It will always be random, and you will always be away from what you have read, okay, what you have learned. So there is always, so this projection becomes an intuitive kind of a way where you can kind of find the distance between this point. Okay, what is the distance between this point and this? It's the shortest path. Okay, that's the shortest path, the distance, right? Let's say we have to drop a particular line from this line, this point to here, and that becomes shortest distance. And the point in which it lands in this is called the projection. Okay, and we don't know. Okay, we don't know how to do this actually. Right now we have a line. We took a random point, and we have a point here. We're just trying to find what is the projection of this point onto this line using this setup. Okay, now you have a system of linear equations, and you can solve for x and y. Okay, which I gave in the number I think in the example of the start of the linear algebra. Let's say you have two equations like x plus 2y is equal to 4, or like 2x plus 3y is equal to 6. You can write it in a matrix form like 1, 2, 2, 3. Okay, and you can write it like x comma y, and this is equal to a vector 4 comma 6. Okay, this is the equivalent of matrix notation. This is a linear system of linear equations. You can write it into a matrix notation like this. So in this example here, okay, what we see here is we have -2 comma 4. Okay, and we are just trying to find out, okay, what value of x will give me 2 comma 10. Okay, we are just trying to find a solution for this. Okay, trying to find a solution of x in such a way that we can solve the problem. Okay, so in case of the other example which I gave you, two linear equations. So anytime, I mean, if you call there is a solution, it has to meet at some point actually. So let's say we have two lines like this. Okay, and the solution for this two lines is this point, because two lines meets at this point, so there is a solution for it. So let's say in this example it is 0, this is 4, 0 comma 4 is the solution, which means x is equal to 0 and y is equal to 4 is the solution for this equation. But in case of this problem where we have -2.4 is a random point in this line, and we have 2 comma 10 as a point for which we wanted to find whether there is a solution, you will not find a solution because it is not part of this line. Okay, even if you try to solve this, it will have like -2x is equal to 2, then 4x is equal to 40. Okay, 4x is equal to 40, then x is equal to, here it is like -1, and x is equal to like 2 comma 10 -2 comma 4, it is like 4x is equal to 40, and it is like 40 by 4 is equal to 10. So you have two contradictory values, which is not which is not a solution for this equation. So you don't have a solution for this, a perfect solution. So you have a system of inconsistency actually. So what it really means is that ax, this is a, this is x. Okay, ax, if this is equal to b, then you have a solution. So now here ax is not equal to b, but we are trying to find out what we can do to make this work. So what we can do is, using linear algebra, you can try to solve this equations, which is now unsolvable because it gives different, sorry, 10 by 4 is 5 by 2. Sorry, this is 5 by 2. This 10 by 4 is 5 by 2. Okay. So we have two x's actually. We cannot have two x's, which kind of solves this problem. So we have a situation where we have a system of equations which is not solvable using ax equal to b. Okay. Now let's try to make this Let's try to solve this problem actually. So what you have in linear algebra is you can take, if ax is equal to b is something as an equation you wanted to solve. Okay, in the other example, in the start of the linear algebra classes, I gave you an example where we used elimination methods and we tried to strike out x and y, and we found out the values of x and y. Okay, and here in this example we will try to use the matrix way of solving the same problem. There are two ways to solve it. We will use the matrix way. What matrix we suggest is A transpose x. If you try to take the transpose of the matrix A and multiply with it, okay, and if you try to take the transpose of the matrix on both sides, you will be able to find a solution for x. That's what the linear algebra says actually through matrix notations. What it really says is you take the transpose of the matrix and multiply on both sides. Okay, and if you want to solve for x, x becomes A transpose. If you take this transpose here, it will be A transpose. Okay, well, before going there, we will try to multiply this. Okay, we will say what is A transpose? Okay, minus 2, 4 is the point we took. Okay, that is A. Minus 2, 4 is the point we took. Transpose is nothing but if you rearrange rows to columns and columns to rows, that is the transpose. Here minus 2 and 4. Okay, this is the transpose. This is A transpose. This is A. Okay. Now, if you see here, we have, this is the original point in the x in the y is equal to x line. Okay, we took a line here, and that was like y is equal to minus 2x is the equation of straight line. We took a point here, that is minus 2, 4. Okay, and this is 2, 10. This is the point we are trying to find out whether there is a projection which you can find. Okay, now we took a transpose of this actually. So what it becomes is minus 2, 4. Becomes the columns becomes rows here. If you multiply this, it becomes 4, like matrix multiplication, 4 plus 16. Okay, 4 plus 16 x is equal to, here also it becomes like minus 2, 4, and it becomes, what is b? B is 2, 10. So 20x is equal to, or it becomes minus 4 plus 40. Okay, so x is equal to 36 by 20. So x is equal to this is like 1.8. Okay, x is equal to 1.8. If you see here, we find x is equal to 1.8. So we were not able to find a solution for x here actually. We are not able to find the solution for x here in this method, because it was conflicting with each other, minus 1 and 5 by 2, and we are not able to get a solution. But if we use this method using A transpose of x, we are able to find x actually. Now, what is x actually? Now x does not tell you the point here. Now ax is what is equal to b. Now if you multiply this 1.8 with a, okay, what is a? A is minus 2, 4. So minus 2, 4 into 1.8 is, I write it here, is equal to ax. This is ax actually. Okay, ax. This is x. A is minus 2, 4. Minus 2 into 3.8 is minus 1.8 is minus 3.6. Okay, and 4 into 1.8 is 7.2. Okay, so we get two values of x and y. Okay, this is what, this is x, this is y. So minus 3.6, minus 3.6 is in this direction, and the 7.2 is in this direction. We get a point here. Okay, this is the point which is the projection of this vector, which we were not able to find out a solution, and we are able to find that this is the point. Now the question is this the shortest point? And if you take this distance from this to this, you will find that it is the shortest point. So we were able to find a projection of a point 2, 10 onto the line using randomly picking like a matrix which values 2, 4 on this line, and trying to find the value of x for which this can be solved. Okay, so we are trying to find a linear transformation. Okay, so linear transformation is nothing but a matrix multiplied on a vector is a linear transformation. We are trying to find out which matrix Okay, if I multiply with a point in x, it will give me a solution, and in this case not a perfect solution but a projection. Okay, so if you multiply the the vector the matrix minus 2 comma 4, which we randomly chose, with 1.8, that is in the domain, it will be able to map it into the codomain. So this is the domain, which is x is equal to 1.8. Okay, that is the domain. And if you try to multiply with this matrix A, that is minus 2 comma 4. Okay, this is x, this is A, I mean it's ax actually. This is doing a linear transformation on this, and it takes you from here to this point. Okay, so ax equal to b is what it really means. You're taking a value from a domain that is a single dimensional domain. This domain is one dimensional because it's just value x is equal to 1.8, and we're able to find a projection that is minus 3.6 and 1.2 in the y direction, x and y direction, which is the projection. So this is how a projection is used. This is how the projection is done or calculated for a point. Actually, you can now repeat it for all the points you have in the data and try to project it into the line, and now then this becomes your point of you can do the analysis once all the data is projected in this line. Okay, you can see what is the average, what is the variance, covariance, everything if it's projected in this line, and you can find whether this distance is large enough or short enough to kind of project it. Okay, if you try to project something very far from each other into a line, it may not get you the good representation of the data. For example, let's say you have data like this. Okay, data spread across like this. Okay, spread across like this. Okay, if you try to project into x-axis, then probably it captures all the variations here. Okay, it captures all the variations here, and this gives you the maximum variation of the data. Okay, and if you try to project it into the y-axis, probably it will be projected like this, and this represents, like, probably it will not. If you are given a choice, okay, if you take this projection or this projection, it makes sense to take this projection because it captures the maximum variation of the data in the x direction. Okay, and if you take this projection, even though it is projected, it does not capture the entire variation of the data because it is like kind of narrow. Okay, this entire data set, if it's projected in x-axis, let's assume that this is a projection axis, and if it is projected here, you capture the essence of the data a lot more than if you take axis like this, which is projected in y direction, because it kind of reduces the entire data to a small width, which does not give you the entire talk about the entire variation within the data. This one probably is much explains the data variation data more. Okay, so between these two, probably this projection is better. So this is what you do in principal computer analysis. Try to project into multiple axes and try to find out which variation is kind of talks about the original quality of the data. Okay, and then you use that as a principal component. And if you see, everything is getting related now. Okay, so linear algebra talks about matrix vector multiplications and your linear transformations, and then after linear transformations you kind of do projections. Okay, and if you do projections, you are able to find the shortest point between the data points and the mean. Okay, or any axis if you want to project, and try to kind of break down the complex data into simpler dimensions which you can work with, and kind of make use of it. Okay, that's the idea of projections actually. Okay, thank you. There is one more way which I will also explain to kind of get the same answer. Okay, through the cosine method. I'll show it in a minute actually. Let me erase this and show it here.